So say if I got a wire of copper. Yeah, just for our example, say if I got a wire of copper, and say if it's like a pretty thin wire here, and I bend it, I twist it, not twist it, I bend it up. So I kind of bend it up, and then I kind of bend it down. So yeah, just applying force, bend it up, and we bend it down. What happens if we repeat this over and over again? Bend it up and bend it down, bend it up, bend it down, and so on. What ends up happening is that even though the material would never like plastically deform, imagine you didn't even like actually plastically deform it, so it would always come back to this nice flattish shape. What ends up happening is that the material ends up just snapping. Eventually, like with enough bends up and down, it ends up snapping. Even though this material was always within its elastic zone, it still ended up snapping. It didn't actually reach like fatigue, stress, or strain. Yeah. Um. So how do you describe what goes on, what happened over there? This is a phenomenon known as fatigue, and a lot of the time this happens without much warning, because again, this is all in your elastic region. There's no like necking of any sort. There's no problem. It just seems that um, fatigue happens out of nowhere. That where you just apply a load, and then just rest the load and apply a load, rest the load again and again, which ends up in fracture. So the way that we describe fatigue is that it results from a bunch of cyclic loading, where you apply load and take away load a bunch of times, and then that's what ends up happening. Quite a lot of structural and engineering failures, like aircraft crashes, structural just damage, just happen because of stuff like this. So the way that we describe like the loads here first is that we can describe it in some sense like analogous to a sine wave, but not really. Where if I take like a stress and over time, so you'll end up with like just a starting stress, and then like it just goes up and down and up and down and up and down and so on until it breaks. Yeah. The way that we describe this is like we have like imagine like a middle like equilibrium sort of amount, the rest sort of, and so similar to a sine wave, we're going to have like the middle, which is what we call like the mean stress. Mean, sorry, I should write that clearly. Mean stress, and that's like the middle, and the way that we imagine this is that this is the max, and the bottom is like the min. Yeah, minimum stress. And so we can get like a mean, which is simply like a normal mean where you take the average. So the average of the maximum stress plus min stress divided by 2. So yeah, so you take this almost the same way as like a sine wave. So we can also have like a range, which is just the max minus the min. So it's like, yeah, the complete height between the two. So that's max minus min. And then likewise, we can also have a stress amplitude, which would be uh, the range divided by 2. Divided by 2. Yeah. So the way that we tend to do things is that we want to compare this stress amplitude against time. Because if there's a higher stress amplitude, then what that means is that it's going to break much faster, because you're applying a greater amount of stress of variance, and it's not going to get used to it. It's like, yeah. So imagine you're bending it more and like even more and even less. So I don't know, like for another example, I had like a bending like more and then bending like less. So like a really sharp bend. That's probably corresponding to a high stress amplitude. We also have a stress ratio. We'll call that R, which is the minimum divided by the maximum. Often you would be given this like for an exam, but just in case they don't, good idea to remember these. Max, yeah, min divided by max. So that's a stress ratio. Yeah. Okay, so now in regards to this stress amplitude against the number of cycles, so this is a sort of logarithmic scale where what we have is, say if I have my number of cycles, so cycles as in how many times you go up and down, right? Yeah, and then this is the stress amplitude. So generally, for a small number of cycles, like the number of cycles that you can take before fracture, it tends to be like a sort of like a 1 over x shape, but this is a logarithmic scale. So this goes 10, 100, 1,000, and so on. Yeah, like 10,000. And yeah, I'm running out of like space and zeros. But yeah, I forgot to fit a 1 in there somewhere, but yeah, you know what I'm saying. And so here we'll end up with this sort of looking shape. Yeah. This is with most materials. Some materials have like a minimum fatigue stress, sort of, so to speak, where it looks almost the same way, same axis, same bottom and top, where it will have this sort of thing, and like it kind of curves a little, and then it goes straight across. I know it's like a little tilted, but like don't mind it. Yeah. So imagine it's straight across. Even so, that's going to be, you can call this like your fatigue stress. That's like the asymptote. Anything more than that, then eventually, after some amount of time, yeah, so anything more than this fatigue stress at some amount of time is going to break. Below that, then it's perfectly fine, basically indefinitely. That's N. That's stress amplitude. So what you could be given in exams is simply like values for this stress amplitude and the number of cycles until failure. So should make this clear somewhere. Fit it like right in the middle. N equals the number of cycles before failure. Failure in our case is like fracture before it breaks, because as engineers generally we don't want things to fail. Yeah, that would be about it.